Hello again. I'm happy to see you that you are here after the coffee break. And we are going to continue with the last part of the session that is dedicated to entrepreneurship, different companies that are devoted to sensors. And we are going to begin with Oleg Pafik that is an industrial engineer from the Public University of Navarra. He has 6 years of experience working with gas sensors in the field of breath biomarker analysis, at first as a collaborator from the Public University of Navarra, and then as a researcher engineer for eversens. This company, eversens, has developed evernoa, a device that was presented on the market on 2017. This device provides a minimally invasive, fast, and simple way relevant information about airway inflammation. This information is useful in the diagnosis and monitoring of inflammatory respiratory diseases such as asthma, as we'll describe Oleg now. Thank you, Oleg.
Thank you. Well, I'm Oleg, and in the following minutes, we are going to see some aspects about the gas sensors that I have experienced myself. So I hope you find it interesting. First, we are going to present ourselves as a company, presenting our device, and see for what we use these gas sensors and what conditions we face when implementing these solutions. Then I will present you some laboratory non-idealities that I have observed when I started working with these sensors. And with these initial results, there are first steps and our first falls. And I think they can be illustrative of the necessity to understand these sensors when using them and not just trusting the obtained results. This experimental work, initial experimental work, will be combined with theoretical background in order to explain them. And finally, some field non-idealities will be commented based on these insights. So this way, I hope we will see what could happen to our sensors and the necessity to protect them against some contaminants and other factors that can make them fail. So I work for eversens. This is a company that was born in 2015 as a spin-off of this university in these laboratories. And back then, I was studying my master's degree in industrial engineering. And I was hired to collaborate developing the sensing elements. So in 2017, we developed our main current product, evernoa, is this one, that measures nitric oxide in the airways. The origin of this company starts with the medical necessity to measure different exhaled gases we have in our exhalations because they can be correlated with some health issues. In the case of nitric oxide, for example, this is a biomarker. These gases we have in our exhalations are called biomarkers, breath biomarkers. So the nitric oxide, for example, is associated with a higher level of nitric oxide in our airways when we exhale, are correlated with a higher inflammation in our airways. So it's used for monitoring and diagnosis of asthma. So this is our device itself. It also has a flow sensor in order to measure the flow of our exhalation. It can be shown at both faces of the device on a screen for the physician and another one for the patient, a bigger one with an LED screen. Also, it contains all the pneumatics, the electrovalves and pumps that direct the air to the sensor, which is this one. It's an electrochemical sensor. It also contains all the electronics that controls the screen, the communication, the Bluetooth, the pneumatics, and so. And then there is the sensor that has its proper PCB with the conditioning circuit, because normally these sensors has a shorter lifetime compared with the lifetime of the device. So this way we can provide the customer the opportunity to change only the sensor when this lifetime is reached. So this sensor is an amperometric sensor. It generates electrons when there is this reaction. The main reaction is the conversion of nitric oxide to nitrogen dioxide in the oxidation reaction. It generates protons, converting the water also in protons. And in the other part, in the reduction that occurs in the counter electrode, the oxidation reaction occurs in the working electrode, this one. And also, well, I will explain later the auxiliary electrode. So the reduction in the counter electrode converts the oxygen with these protons that were generated in the electrolyte to water. So as you can see here, it's important to have water and oxygen in this reaction. It's not just a sensor that measures the nitric oxide. This is like an obvious thing, but maybe when you start making your tests, maybe you don't have this in mind, and this can have some results that we will see later. So these different places where the reactions occurs make a movement of charges. One part is the electrons that move through your circuit and the protons that move through the electrolyte. This is also important, as we will see later. So then some reactions in the electrochemical gases, for example, the nitric oxide, are non-spontaneous, so you have to apply an overpotential. This is done with a third electrode, the reference electrode. In this case, for the nitric oxide, you have to apply this voltage. And in this electrode, there are no reactions. It's just to put a voltage in this solution in the electrolyte, because there are a gradient of voltage between both electrodes. So if you place a reference electrode near the working electrode, for example, you can ensure this potential. And then there is the fourth electrode, the auxiliary electrode. It's not in every sensor. In this sensor, in this electrode, there are the same reactions as in the working electrode, but excepting the main reaction, in this case, the nitric oxide reaction. So, for example, it's useful to have separated the temperature effects or other gases that can react in this signal. So then you subtract them in a differential application or stage, and you can have only the part corresponding to the nitric oxide, the main analyte you want to measure. For example, in the case of carbon monoxide, typically the working electrode reacts to both carbon monoxide and also to the hydrogen. So in this case, if you place an electrode that only reacts to the hydrogen, you subtract that signal and you obtain only the signal of the carbon monoxide. As you can see, well, the current is converted to voltage, then amplified, then converted to digital information. And also you can see it's really important, the filtering stages. There are a lot of work on filtering the signal, because in some cases, there are like really low concentrations, there are really low currents. So it's a really an important part of this. And also there is the potential stat that generates the electrons that the counter electrode needs. In general, they proceed like the whole circuit is connected. So the electrons that are taken from here finally goes back. So the electrolyte is in equilibrium. And also it monitors the reference electrode. So it charges or discharges this electrode to maintain this overpotential. So when we started working, the first thing I encountered was this gas panel. And typically, the typical setup was to buy the sensor, buy the bottle of gases you wanted to measure, mix it with an inert gas, for example, the nitrogen, the inert gas, mix it in a radio to generate the concentration you want, and then apply it to the sensor. But as we have seen, you need humidity and oxygen. So in this case, these bottles were dry gases, and we had this response. As you can see, the first measurements were okay, but finally there was a shift in the baseline. And this is because in the reduction reaction, when the oxygen started being scarce, the lack of oxygen generated that the reduction reaction produced hydrogen instead of water. So the composition of the electrolyte changed, and that's why we had this shifting. When we added some oxygen from a dry gas bottle again, we obtained a flat baseline, better results. But if we see the sensitivities we obtained, the experimental ones with different sensors were still different compared with the theoretical sensitivities the manufacturers told us. In this case, the minimum specification was twice as the experimental results, and the maximum sensitivity was like 4 times bigger. So we continue to study this. The next thing we started using was this nitric oxide generator. In this case, the nitric oxide is generated through the photolysis of nitrous oxide, with a low pressure mercury lamp, and then mixed with ambient air taken from the environment. We filtered with a nitric oxide scrubber and mix it. So in this case, we obtained sensitivities higher than the previous one with the gas panel, but they were still below the theoretical. But here, what we can see is that humidity is also needed. As you have seen, the electrolyte needs water. So if you expose it to dry gases, finally it can dry out, and we will profound that, deepen in this. So first, you will have to understand that the electrolytes gain or lose water when exposed to different relative humidities. In this case, for example, some sensors, this process can be very long and take up to a month. But this process is also influenced by the hole size, the exposure of the electrodes to the gases. So if you want to detect really low concentrations, you have to maximize the exposure of the electrodes to the gas, and this means also a bigger exposure to the ambient air, and therefore with sensors for low concentrations, this process can take just 2 hours. So in the case of the experimental tests we had, maybe in 2 hours we have a lower sensitivity because of this. Manufacturers normally say that under 15% of relative humidity, the sensor could dry out and give no signal at all, or maybe decrease its sensitivity or increase its response time. And it also depends on the sensor, as we will see later. And also there are an upper limit, because if there is typically above 90% of humidity or 75% of humidity, the water the sensor gain could be, it can increase its volume 3 times bigger and break the enclosure of the sensor, and finally provoke an electrolyte leakage, and give no signal at all finally. So in this case, for example, you have the carbon monoxide. When it's dehydrated with 0% of relative humidity, the response time increased, but the sensitivity stay constant. And conversely, the hydrogen sulfide, the response time remains constant, but the sensitivity decreased. So it depends on the sensor. And this is because when the sensor loses this water, the acid concentration of the electrolyte increases, and finally it impedes the ion mobility of the protons. So this is, like you see, it's a circuit. So if you model this, finally it's like a resistance, and as it's also can be seen as this slope in the voltage gradient in the electrolyte. So finally, if you model this, the circuit is that with a high resistance, there are less current generated and therefore less sensitivity. But there are also capacitances. As we will see in the next slide, it's the double layer capacitance. So if you increase this resistance, the charging of this capacitor is lower. It's like a low pass filter. So that's why the response time of the sensor increases. So this is the double layer capacitance. It happens when you have in contact an electrode with a solution. And this is because when you charge, for example, the overpotential of the working electrode, there is discharging the charge of the electrolyte line up with the interface with the electrode. And this can be up to between 50 to 200 millifarads. And in practical terms, this can be like 1 day or 2 days in order to be able to see the detection of the analyte gas. But if you want an optimal performance, maybe it can take up to 1 week or 3 weeks, because as we will see later, it's a potential equation. So here it is, because all this current that charge the double layer capacitance is seen in our circuit. So the most of the charging occurs during the first hours. But if you want to measure really low quantities, you need to minimize the drift of the baseline and increase the gain of the amplification the most. So for this, you might stop seeing this baseline drift. And this is also important if you commercialize your sensor finally, that the customer needs to understand that these sensors need be powered all permanently. There are batteries and so, but they are not infinite. And also, if the customer will change the sensor, it needs to understand that it can't make a measurement right after. It have to wait the warm-up time. Because, for example, if you disconnect this sensor for 10 seconds, you must wait 40 seconds because of the potential equation of the charging or discharging of this capacitance. So a correct training is needed in these cases, and to be sure that the customer understands this, because when it goes complying to you, it says that there are strange measurements, but finally it's something simple as this. So then the last non-ideality is that when we started using ambient air with the gas panel, we started having the same sensitivities we had with the nitric oxide generator, but we started using these compressors with air tanks and reservoirs. So we saw that when the intermittent operation of the pump was being seen in the sensor baseline as these drops. So here is where the compressor started working, and then the air proceeded from the air tank, and there was another baseline. So now we use compressors without air tanks, but the thing here is that most manufacturers say that when you have a sufficient flow to the sensor, and in normal cases, it's flow and pressure independent. But we checked this, and we saw that the sufficient flow, okay, when up to 100 millimeters per minute, there was the most change in the sensitivity. But then when we were increasing the flow to the sensor, the sensitivity was still increasing. And also this increasing sensitivity was different depending if the flow was coming from the analyte gas flow or the mixing gas. And this is because if we see the conceptual the concepts that lie behind this, we have two types of sensors: the capillary type sensor and the membrane type sensor. Typically, they're a permeable membrane. And the difference can be seen with the Knudsen number. This is a radio between the mean free path of the molecules of the gas and the diameter of the capillary, because in order to obtain a linear relationship between the concentration and the signal that you obtain, the current, you have to make the diffusion the limiting process. So within all the processes that occurs during in the detection mechanism. So if the capillary is big enough, this Knudsen number is low, so you have a normal diffusion, because the main interactions are between the molecules. The molecules rarely impact the wall. So if you mathematically characterize this, you have that it's pressure independent. But in membrane type sensors, there is a Knudsen diffusion because the molecules frequently impact the walls, and that's the main interaction, and it's pressure dependent. So typically, manufacturers use their sensor for other applications, like industrial applications, and there maybe the pressure dependence can be neglected, but we can see here that it's just an approximation depending on a radio. There is no a particular point where there is like a real difference between sensors. So that's what we have seen. So the conclusions are that you need to be sure that all the reactives of the reactions are present, in this case, oxygen and humidity, but in other sensors, it could be another thing. That the electrolyte health must be ensured. In this case, we have seen the dehydration that can change the composition of the electrolyte, but also other gases can dissolve in this electrolyte, such as organic volatile compounds, such as alcohol. During the pandemic, it was a big issue, the hydroalcoholic gels, also cleaning products that includes fragrances and other alcohols. If you are sharing a laboratory with another research group that uses another gas, it also could impact your sensor. A customer could keep the sensor in a kitchen with a gas natural or burning candles, and this all can impact your sensor. So these are something you need to check. Also, the warm-up time, you have to ensure the double layer capacitance is always charged. And the flow and pressure dependence, you must know that this independence is just an approximation, and maybe you have to check experimentally what really happens. So this is all. Thank you for attending this presentation.
Thank you, Oleg, for your talk. So we have a few time for questions. Have you thought of thinking of using other type of sensors instead of this one?
Well, the carbon monoxide we have studied a little bit. There are some differences, as you have seen. The auxiliary electrode is really important. Also, hydrogen sulfide have been studied, but there are some particular problems with the gas bottles that are toxic and so. And that's it. And hydrogen also, but there are a lot of sensors, but they all have some particular things that must be studied experimentally. And at first hand, you don't know everything about them.
Do you know this? Do you know what is the equivalence between these type sensors and the diseases you can detect in the breathing?
Sorry, could you repeat?
I mean, we are detecting NO just to. Okay, sorry, but it doesn't work. It works. Okay. So the idea was that you are trying to detect NO. I mean, nitroxide in the breathing, because this is there is a correlation with something like asthmatic condition. But with these other sensors, there are some other.
Yeah. In the case, for example, well, the nitric oxide is the main one because there are medical guides that tell you what concentrations are correlated when you have a probability of having asthma and when not. But with other gases, for example, the carbon monoxide is an indicator of smoking habits, and the hydrogen and the methane, and so there are indicators of some bacteria you can have in your stomachs, and so normally there are studies with nearly all gases that are correlated somehow with some health issues, but they are not standardized, and they are not there. If you develop a product for that, normally it's like a additional feature or an instrument for for laboratories, but not for medical products normally.
One more question.
So just a question, what is the lifetime of your sensor, like your device?
Sorry, what?
Lifetime.
The lifetime.
Yeah.
Normally, it can be 2 years, 3 years, something like that. And the product can last 5, 6 years.
Yes, thank you.
In your experience, what was the optimal humidity level, or your sensor can cope with any humidity level?
Well, typically, the most attractive relative humidity is the indoor humidity of 50% and so. But at 75%, 25%, it's really okay. And also intermittently, as you have seen, it's a process that can take up to several weeks. So depending on the sensor, it can stand another extreme humidities.
Okay, so we have one question for online. So how much oxygen level is required?
Yeah. That was the graph I showed, this 4.2% of oxygen. I think it was an equation I made 6 years ago. That was the percentage needed for the reaction, but I don't remember exactly. I think it was something with this reaction that with moles and so I made. So this could be the percentage of oxygen, but I can't be really sure to state that.
Any other question? Let's thank Oleg again.